So all those groups are known to be simple. So your mother proved that this group is simple for R different from the dimension of the manifold plus 1. And there is a failure in the proof in this regularity. And this is a big open question, whether in this particular class, let me call this N, whether this group is simple. Simple means algebraically simple, so there is no non-trivial normal subgroup, no proper normal subgroup. This is one of my favorite problems, actually, whether the group of C2 diffeomorphism of the circle is simple. From the 90s, I think. It's a very nice theorem that says that if one takes a isomorphism between groups of diffeomorphisms, and isomorphism, then actually the manifolds are the same. Okay? The regularities are the same, and there is only one way to produce such an isomorphism, which is the obvious one, is to take a diffeomorphism of the manifold and to conjugate maps. Okay? So there exists a CR diffeomorphism of the manifold, well, R equal to S, such that phi of a diffeomorphism is just the conjugacy by this map. Okay? So the question, so the general, say, program here is, can we distinguish groups of diffeomorphisms by looking at finitely generated subgroups? Theorem by, I think by Kim and Coberta. Which says that the answer is yes in dimension 1. So for every R at least 1 and S strictly larger than 1. So here, let me say that, well, you can think about the exponent as integer numbers, but actually you can also consider intermediate classes of differentiability. You can think about the derivatives in some suborder spaces. This still gives groups. You can think about Holder scales in the middle and so on. But if you want to keep in mind something which is more transparent, you can think about integer numbers. But this theorem is totally general. It says that for every R squared than S, there exists a group which depends on this parameter, such that this group embeds in the larger group. The larger group is the group of a smaller regularity of the interval, but doesn't embed into the larger group. And actually they manage to do it not only for the closed interval but the circle. But actually this is the crucial part of the okay. So you can distinguish the differentiability classes of these groups by looking at finitely generated subgroups. It is very good to consider what are called length functions. What is a length function? It's a function from the group into the reals that satisfy this property of subadditivity. So we would like to have this. This is a length function in a group. But let's suppose that we are in class C1 and M is any manifold, say compact. Well, for this case, there is a length function. So you take L of f equal the logarithm of the norm of the derivative, but the norm in the continuous setting. So the sup of the norms of the derivatives, and you take the logarithm. This is a length function because of the chain rule. This is a length function. Okay. To answer. So let me just say something. When you have a length function on a group, there is a procedure to consider what is called the stable version of the length function. So because of this inequality, we have that for every element in the group, the length of f to n plus n is smaller or equal than the length of f to the n plus the length of f to the n. Okay? And whenever you have this inequality, there is a classical lemma by Fekete that says that, and there exists the limit of L of f to the n divided by n. This is totally general. If you have a length function, then you have this, and you can call this, say, L infinite. The stable version, the stabilization of the length. So it may happen that the length of an element is positive, but the stable length is. For instance, in this case, L infinite of f, well, this is the logarithm of the derivative of n divided by n, is somehow the Lyapunov exponent. Okay? This is called, what is called the maximal Lyapunov exponent. Okay? And so with this approach, you recover this classical object in dynamics. When we have finitely united groups, there is a length which is obvious. You fix the system of generators, say G1 up to Gk, and you denote, well, this is Gromov's notation. So the norm of f, well, the length of f, or the norm of f, is the minimum value, minimum number of generators that you use in order to write the element, okay? The minimum number of factors that you use among these generators. I suppose that the generating system is symmetric, so that I can use only positive powers. F is distorted if the corresponding stabilization of the norm for f is vanishes. If the limit of the norm of f to the n divided by n equals to c. Gromov proposed the following definition. Let G any group say that an element in G is distorted. Before that, so the length of the group elements depends on the system of generators, but the property of being distorted doesn't depend on that, because if we change the length, well, they will change in a Lipschitz way. So, okay, so a group element inside any group, there is no geometry a priori in this group, but you will say that an element is distorted if it is distorted inside some finitely generated subgroup. Okay? So this is an example of a very big group. Why it is interesting? It is because every countable group sits inside the group of homeomorphisms of the Cantor set. This is, you think a little bit, if you take, say, if you take gamma, any countable group acts on this product just by shifting coordinates. And if gamma is infinite, this is a Cantor set. So every group sits inside the Cantor set, the group of homeomorphisms of the Cantor set. So if you think things dynamically, you may think that all the group theory is inside. Okay? And actually, this may seem very naive, but actually many important groups have been discovered as group acting on the Cantor set. Okay, so what Eve notices is that in this group, every F is distorted. It's a very nice argument. Take G, the group of C1 diffeomorphisms of any manifold, but C1, and take F in G with an hyperbolic fixed point. Then F is undistorted. Okay? There is a theorem by Artur Avila, a very nice construction that says that for every irrational angle, the rotation by this angle is distorted in the group of C infinite diffeomorphism of the circle. So given R, again smaller than S, so does there exist a diffeomorphism of class CS and given a compact manifold? Okay, say this, such that first thing, F is distorted in the larger group and F is undistorted in the smaller group. There exists a C2 diffeomorphism of the circle, of the interval, sorry. Actually, the diffeomorphism of class C infinite. And there are many. It is distorted in the group of C1 diffeomorphisms. And it is undistorted in the group of C2 diffeomorphism. And how do I prove